Okay, let's get started. So, how many of you have questions since last time? What's due Friday? Homework. Any questions?
Yeah.
Yeah.
Um, so.
Actually, I might as well just pull it up. Yep. Mm-hmm.
So I read through the Slack questions that were asked yesterday.
Mm-hmm.
Though I'm still kind of fuzzy as to how to automate, I guess, the covering array because
Mm-hmm. Like for which question?
For the first one.
The first one should be, you're all thinking way too hard. It should be really easy. It's way easier than you think. So, what does it say to do? In fact, could I just scratch out the word covering there and just say the exhaustive array? Ignore covering. Could I do that? Yeah, why?
Because whatever, as long as it works.
Well,
As long as you don't need to optimize anything.
right. Yeah. If you have every possible row, does a covering array have to live among those? So is every interaction covered if I just have every possible row? I just brute force every row. Yeah, it must be. So you don't even need to think about covering here. Just write every single possible row. That's all you need to do. So what is one possible row? Let's just say the values are 0, 1, 2, and 3. But they could be anything you want.
0, 1, 2, 3, 0, 1, 2, 3.
Even simpler than that.
Zeros.
Just zeros. Zeros is one row. And how many zeros am I going to have? 8. Why? Because there's 8 columns. Good. What's another row?
All ones.
All ones. Another one would be all 2s. All 3s. Oh, these are all the possibilities, right? No. How many more possibilities are there? Are there a few more or a lot more? A lot more. What's another row?
0 and 1. 0, 1, 2, 3, 0, 1, 2, 3.
Yep. Is there any particular pattern that these values need to be? No. Why? Because we're making every row. Okay? If every position has 4 possible values, don't answer this, but because it's the question, how many possibilities are there total if every single one of the 8 positions has 4 values? Is it 32? No. So that's what the question is for. This should be the easiest question. You're thinking way too hard. Any questions about question 1 then? You should be able to write a very simple program like 10 lines that does this. It should not be hard. Okay, any other questions about the homework?
So for the verifier,
Mm-hmm.
you mentioned for number 1, you mentioned that you just want us to include a few sample rows from
Yeah.
the covering area.
Mm-hmm.
We want to just write a simple function or whatever to generate it. So
Yeah. Mm-hmm.
number 2 then have to verify for the array we're verifying. Are we just verifying those few rows, or do we verify that entire exhaustive?
It must be the entire exhaustive one, because if you just have a few rows, these 5 rows are not a covering array. So you're just including a few so you don't include thousands and thousands of rows in your printout. That's the only reason.
Okay.
So, but you'll just save it into a file because it's just easier to handle in a file, and then you read the file. Hopefully you know how to read a file at this point. So read the file, and then you verify You read it into a two-dimensional array or whatever structure you want, and you just verify it that way.
Okay.
Other questions? Yeah.
So, we kind of talked about this on the Slack last night,
Mhm.
but I'm still kind of confused. So, if like your T is like strength 3,
Mhm.
then can't you choose any random 3 in any position of the array?
Exactly.
So then, how do you avoid repetition that way?
Repetition of what?
Like testing among the 3. Would like it be for? So you'd have to choose the same 3 for every row.
So let's actually just go through what a covering array is. So it says that every interaction appears at least once. That's what the definition says to do. So what do you do here? Well, we have to look at every interaction. Well, what does an interaction involve if T is 3? Well, it involves 3 columns and 3 values attached to them. So how many choices of 3 different columns are there here if there are 8 columns in total? I actually don't know the number offhand, but it's 8 choose 3. That's the number of possibilities. I don't know the exact number offhand, but that's what that is. Yeah, so that's the number. Oops. Let me turn off Wi-Fi so I don't get notifications. Number of choices for 3 distinct columns. So one possibility will be in checking the first 3. I can be checking the first 3, or I might check the first. Oops. I gotta move it down. It thinks I'm gonna start typing. Oops. I like Notability, but sometimes it's a pain. So I could be checking the first 3. That may be a choice of columns I choose. I also need to check, say, the first, the third, and the fourth one. I might check the fourth, the fifth, and the sixth one. Any set of 3 columns, I need to check all possibilities, all choices. So this 3, this 3, this 3, these 3, every single choice of 3, I have to do a check on. Okay? Well, let's just say I pick 3 columns. What do I have to do?
You start with once you have 3 columns, that's its own kind of array. So you basically go row by row there, and each row would represent would be a straight 3.
Yeah, so 3 symbols. Yeah, so 3 values. So what I would have to check is, in these 3 columns, is 0, 0, 0 in there? Is 0, 0, 1 in there? Is 0, 0, 2 in there? Is 0, 0, 3 in there? Etc. for all 4 times 4 times 4 possibilities. Okay? So I would check, say, for the first 3 columns. I would see, okay, 0, 0, 0 is in there. Check. Is 0, 0, 1 in these first 3 columns? No. So what can I conclude about these 5 rows here? Is it a covering array? No. Because that one interaction, these 3 columns with 0, 0, 1 ain't there. Okay? But suppose I checked every single set of 3 values for these 3 columns only. Those 3 columns. Don't I have to check other sets of columns too? Yeah. So once I'm done these 3 columns, I move on to the next set of 3 columns and do the same check. Move to the next 3 columns, do the same check. And then if I go through all 8 choose 3 possibilities and all of them said yes, what can I conclude about the array? It's a covering array. Okay, does that help? Yeah.
So the verifier then is basically just breaking. It's just you have your covering array. You start picking any 3 columns that you haven't picked already, and then you would go row by row in that like subarray sense, and then to see if every 3 tuple row
Yeah.
is, well, is it a 0, 0, 1, 0, 1, 3 a possible 3 tuple,
Mm-hmm.
and you want to see that all of the 3 tuples are accounted
If they appear somewhere in some row somewhere.
for. Yeah.
So like if I was looking for 2, 2, 2 in the first 3 columns, I would see, in row 3, it's there. As long as it's somewhere. That's all that matters.
But if there is if you finish it as a 3 tuple that's just not in that's not a row, and any 3 columns join together, then
It's not a covering array.
all right.
Yeah. For the generation of like getting the 3 distinct columns, you could hard code it if you wanted to, but you can just write 3 nested for loops. One loop is going over the columns for the first column choice, and then another loop for the second column choice, another loop for the third column choice. It should be like 10 to 15 lines. It shouldn't be hard to do. There's probably some miscommunication, but I intended these to not be difficult. Any other questions on the homework? Oh, and questions 4 and 5, you don't have to turn those in. It's not like bonus points or anything. It's just to get you thinking, but you don't have to do them. I guess there's 6 or 7, but any other questions about the homework?
So if you choose to do anything, you don't for 4 and 5. If you choose to do them, you print them out both 6 and 7. If you choose to do them, it's just for thinking.
Yeah, it's for your thinking, because actually 6 and 7, there isn't an actual fixed answer. Whereas for 4 and 5, that there is an actual answer to the question. Whereas 6 and 7 are research level types things, because there are different techniques of what you could actually do. So that's why. Any other questions?
One last one.
It can't be just Bilal all the time. Okay.
I'll stop after this.
No, it's excellent. Great.
Since there's no practice problem session today, would you be around your office just for questions as they come? 10:30 or 11:30, or-
Actually, that's a good thing. Would you be interested in a problem session today? I see like 4 heads nodding. Who is interested? Okay, so I think we should have one. So it might be interesting to bounce ideas off each other. So let's have a problem session today. But I will be in my office, but I don't have office hours.
Okay.
So yeah, that's all I have. But I will be on Slack available and all that. Okay, so let's go back to stuff. Okay, so last time we started talking about the basic things involving covering arrays, which are all of the ways that we want to actually make these things. So we first started talking about these lower bounds, about if we don't know the exact number of rows, which is optimal, well, can we bound it from below and above so that we know we must have at least a certain number of rows and at most a certain number of rows for the optimal answer. And we derived last time that for the covering array number, where we have v values for every column, we must have at least v to the t rows. Because if you look at any t columns, each column can have v different values, so the number of interactions in those columns is v times v times v times v times ... t times. So it's v to the t. So I must have at least v to the t rows. So then we started to ask questions about, well, can we get that optimal number always? If I give you 5 columns versus 100 columns, can we always get v to the t rows? Or is it just not possible? And it turns out to not always be possible. And in fact, on a very small percentage of numbers of columns can we actually get that exact number. And we may talk about why that is. But at some point, the number of rows must grow. And we'll actually prove that today. So what we looked at last time was these two statements, the second and the third one, which are basically just saying the optimal number of rows for an arbitrary strength, arbitrary number of columns, arbitrary number of symbols must be at least as large as if I make the strength 2 and the number of symbols 2. And why is that? Well, what we talked about last time was this example down in the bottom right. If I have a higher strength, then I still have a covering array of strength 2, because if I look at any 2 columns within the T columns I have, then I must be able to see all 2 tuples in there. So 0, 0, 0, 1, 1, 0, and 1, 1. So if I have strength T, where T is just something bigger than 2, then I have a covering array of strength exactly 2. Because it's the exact same array is an array of strength 2. Then we looked at an arbitrary array of strength. Go ahead.
Sorry, can you just repeat what you said about strength T or T?
Yeah. As I was saying it, I felt that it was really convoluted to say. So no problem. So what the first line is saying, the second bullet point is saying is that if I just have an arbitrary covering array, so strength 2 or 3 or 4 or 5 or anything, just arbitrary, and I take the exact same array, don't modify it, except I view it now in terms of strength 2, not the arbitrary strength, but just strength 2. Well, if T is at least 2, then I can pick any 2 columns. Then every interaction in those 2 columns must appear, because every interaction in the T columns appeared, because it was a covering array before. So if I take T to be at least 2, and just pick 2 columns out of the original T, all of the interactions in those 2 columns must appear. So that means that if I have a covering array of any strength, at least 2, the same array is one of strength 2. And this little example in the bottom right illustrates this. If I have one of strength 3 right here, so I have 3 columns, and I just pick any 2, say the ones in the red boxes, then those 2 columns have every interaction appearing. 0, 0 is there, 0, 1 is there, 1, 0 is there, 1, 1 is there. And we can actually see why that is because of the arrows that I put there on those 4 rows. Notice that the third entry is 0 in every place. And in fact, if we look at the other 4 rows, so I'm going to put those in purple, what do you notice about the other 4 rows? It's the same thing, because the third entry has 1s everywhere. So if you fix, although this may sound a little complicated, if you fix the other T-2 columns to some interaction, just fix the other T-2, the 2 that are remaining must go through every possibility after we fix those T-2. So if I fix 0 on the third column, the other 2 must cycle between 0, 0, 0, 1, 1, 0, and 1, 1. And the same thing is true if I have strength 4, I fix 2 columns and just look at the other 2. If I have strength 5, I fix 3 and I look at the other 2. And so therefore, if I have arbitrary strength T, I have one of strength 2, the same array, the exact same array. Now, go into the next bullet point, the third one, says if I have a strength 2 array now, this says that if I have just some number of symbols, which can be at least 2, I can change that array into one that has exactly 2 symbols. So, for example, the one that we did up here last time, where we had 3 symbols, 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, etc. Well, what I did was I changed all of the 2 entries into a star. And what star means is it can be fixed to 0 or 1. It doesn't matter what it is. So does this work? Well, if you look at the remaining entries, 0, 0, 0, 1, 1, 0, 1, 1. So in fact, the same array, if you change every other symbol into either 0 or 1, then I get an array with exactly 2 symbols, 2 values. Okay? Any questions on that? So that's what we did last time. Okay, so so let's go to that 4th point. If we get a bound on strength 2 and 2 symbols, then if I have a lower bound on this simple case, then I must have a lower bound on the general case, because I can convert any array of strength T and values V into an array with 2 columns and 2 symbols. Okay, so if I get a lower bound on 2K2, I must get a lower bound. The same bound is 1 for TKV. So let's look at this point then. It says every 2 columns of a covering array with strength 2, 2 values must be different. Is that true? Suppose that I have 2 columns that are exactly identical. What can you determine about them?
They wouldn't be part of the covering array because they wouldn't have all the combinations.
Right, they wouldn't have all combinations. At best, they have 0, 0, and 1, 1. They can't have 0, 1, and 1, 0 because they're exactly the same column, a duplicate column. So, well, if I have, so let's look at this bound over here. And I'll rewrite it over here because it's kind of hidden. K, the number of columns, must be less than 2 to the n. And I put a y there. Why is that true? What is that really saying? The number of columns must be at most 2 to the power the number of rows that you have. Well, if I have n rows, what is the total number of possible columns? If I have a set of size n, what is the power set size? 2 to the n. So why is this true? Well, let's look at this array. What is this array doing in the bottom left? It's listing every possible column. Well, can I put another column there? With 2 values? No, I can't. Why?
Because it would have already.
It would have already appeared. And we just said that a covering array can't have duplicate columns. So the best I can do is list every possible column. Well, is this a covering array? Look at the first 2 columns. What are in the first 2 columns? 0, 0, 0, 0, 0, 0, 0, 0, all the way down until we see 0, 1. Is that, do all interactions appear in these 2 columns? No. So it's not a covering array. So the best we could possibly hope for is the number of columns being less than 2 to the power n. But this is clearly not a covering array, so I can't get away with all columns. So what this tells us is that even if it were equal to 2 to the n, let's just say we could achieve that. Well, that tells us that the number of rows is logarithmic in the number of columns. Can anyone tell me why that's the case? If we look at that equation, and let's just say, just for simplicity, that the number of columns we can achieve is 2 to the n, even though we can't. Why does that tell us the number of rows must be logarithmic in the number of columns? This is like 290 stuff day 1, so this should be easy. Why is the number of rows n logarithmic in the number of columns?
Because if you add one more column, like if you add, like in binary, like if you add one more digit, then it grows logarithmically the number of bits.
You're thinking way too hard. Number of rows n is logarithmic in the number of columns k. How do I solve this equation for n? Take the log, okay? So that's why I keep saying logarithmic. So what is n here? Logarithmic base 2. But for asymptotic notation, does the 2 matter? No, why not?
They grow at the same rate.
Yeah, they grow at the same rate, yeah. Well, the 2 indicates that we're just dividing by a constant. And big O, whatever, those ignore constants. Okay, so this tells us that n grows logarithmically in k, but this line says that it grows at least log k. Why is that? Can we achieve 2 to the n columns? It wouldn't. It's not possible because these 2 columns can't work with each other, the first 2. So at minimum, I have to get 1 away. Well, might I have to do asymptotically fewer rows? I mean, fewer columns. I might. It's just I can't do better than log k. I might be able to do log k. I might need even more rows than log k. So that's why we have big omega log k there. It's at least log k. But it turns out we can 2k2 exactly. So any questions on lower bounds? Yeah.
So like you eliminated the first column, but what if, because like we compared to the second, but could the first column theoretically work like the third column?
It could, but if any 2 columns don't work, then the entire array doesn't work. It has to work for every choice of 2. Other questions? Yeah.
Like point 4, like so how is the lower bound like equal to like the 142? Because if it's for like TKV, wouldn't it be like higher than like wouldn't it be like v raised to t or something like for the lower bound?
So for general TKV, the optimal number of rows might be larger than the one for 2k2. So if I lower bound this guy, this lower bounds this one. If I get an upper bound for the 2k2 one, that doesn't tell us anything about TKV. But consequently, if I get an upper bound for TKV, that gives us an upper bound for 2k2. So it's kind of like a sandwich. If you put the bread underneath the one, then you have bread underneath the top one. Terrible analogy, but any other questions?
So
Yeah.
the lower bound is basically it should say that that's actually I'm just asking, I guess, why are we lower bounding the size of the number of rows?
So this is to see what the growth rate is. That's the only reason we're doing this.
Oh, so the best case then would be log k for the coverage.
Yeah, the best possible thing we can do log k because it's always at least log k. And in fact, we'll even prove at some point later that it is log k. That's the optimal number, is some constant times log k. Other questions? Yeah.
Can you explain the fifth point again a little bit? On the last part, why is the case more than two squared?
Because if two columns are the same, then the best we can do is 0, 0, 1, 1 appearing in those two. But we have to see 0, 1, and 1, 0 at some point.
And so, how does the last part? It's more
What last part?
So k is more than 2 squared.
Because if we just list every possible set of columns, all of them are different. And so if I try to add another one, then I'm going to get a duplicate. And I can't have a duplicate. So 2 to the n is the absolute most possible number of rows I can have. I mean number of columns I can have. Yeah. Okay, so let's talk about 2k2. So, in fact, we know the exact number of rows that's optimal for every choice of columns. So you can say that this case is solved in some sense. So this actually looks a little daunting, and it kind of is, but the thing is that there's a very simple recipe to actually make the covering array itself. So I'm going to talk about the formal stuff first, and then I'll show you the really easy way to actually make this. And you'll use this in your second homework. So something called a Sperner family is basically you have a ground set x. So let's just do a short example. So if x is 1, 2, 3, 4, 5, that's my ground set. And then I have a bunch of subsets of x. So, and I call that B. So for example, I could have 1, 2, 3, and then maybe I just have the set 2, and 3, 4, 5, and then maybe one more. 1, 3. And those are my sets. I just pick a bunch of subsets. You got a question?
No.
Okay. So what we're doing here is we have a ground set, and we just pick a bunch of subsets of it. And what we have here, if it's a Sperner family, then there's no set that we have that's contained in another. So for this B set right here, is there a set that's contained in another one? Yeah, which one? Yeah, the 2 set is inside the 1, 2, 3 set. It's a subset of it. So this is not a Sperner family. What if I just knock that 2 set away? 1, 3, yeah. So 1, 3 is in the other set. Let's actually change that to 1, 4. That's what I wanted to have happen. That was my mistake. So now is it a Sperner family? Yeah. So the sets can have intersection, but it's just that one can't be completely inside the other one. Yeah. So that's what a Sperner family is. So what we're going to do is we're going to form a covering array based off of the Sperner family. And what do? You form what are called the characteristic vectors of the sets. Anyone not know what characteristic vector means? Okay, so let's do it. So here's what you do. So I'm going to rewrite the set right here. So actually, I'll just copy it. So let's copy this set. I'm going to move it over here. Oops, I got some extra. So here's what we're going to do. So we're going to make basically just a Boolean indicator for each of the sets in turn. So I'm going to call the 1, 2, 3, the 1, 2, 3 set, I'm going to call that S1. I'm going to call the 3, 4, 5 set S2 and the 1, 4 set S3. And maybe I'll move them closer together. And what we're going to do is we're going to have S1, the sets themselves be columns, and the rows are going to be the elements of X. So the elements of X are 1, 2, 3, 4, 5. So I'm just going to list those out. And what we're going to do with this is in the S1 column, I'm going to put a 1 in that row if that element is in that set. So for the first row, is 1 in the set S1? Yeah, it's in there. So I'm going to put a 1 there. Is 2 in the set S1? Yep, it is. So we put a 1 there again. 3 is in S1. Is 4 in the set S1? No, it's not. So we put a 0. Is 5 in the set S1? No, so we put a 0 again. So it's an indicator for each of the values, whether it's in that set or not. For S2, what is the vector going to be?
Just
0, 0, 1, 1, 1. Because 1 and 2, those are not in the set S2, but 3, 4, and 5 are in the set S2. So I have 0, 0, 1, 1, 1. And then for the set S3, what will it be?
1, 0, 0, 1.
Yeah, 1, 0, 0, 1, 0. Okay? Any questions on what a characteristic vector is? So you just take the sets, line them up in columns, and you just write a 1, 0 vector. So you can think of it an array or a list or something, where you put a 1 if that element is in there, and a 0 if the element is not in there. That's all it is. Okay? What do you notice about these 3 columns? It's a covering array. Why? Well, think about it. No set is contained in another one. So that means that if I look at 2 sets, they might have intersection, but one of the sets must have something that the other one doesn't have. So if you view it like a Venn diagram or something, each pair of sets must look like this, at least, because it's not the case that one is contained inside the other one. So they might have intersection, but there's always something on that one set has that the other set does not have. What does that tell us about the characteristic vectors? If you look at those 2 columns, there must be a 1 and a 0 somewhere. And consequently, there must be a 0 and a 1. If we look here, well, do we see that? We'll look at S1 and S2. We see a 1, 0, which means that there's something in S1 that's not in S2. But do we see a 0, 1 somewhere? Yeah, because there's something that the other set, S2, that S1 does not have. Well, is 0, 0 in those first 2 columns? So is this a covering array? Shoot. What could we do to fix that? In fact, well, actually the other 2 pairs do have 0, 0. But what is a simple way that I can ensure that 0, 0 always appears? One of you.
Just add a row of all zeros.
Exactly. Add a row of all zeros. That covers the 0 problem. I claim that 1, 1 doesn't have to appear. Shoot. Why is that? Well, Suppose that I added a fourth set to our collection here. How are we doing on time? I'm going to add the set 4, 5 to our collection. And I'm going to call it S4. Now, go ahead.
Should you also change this to? Or does that matter?
I'm not sure what you mean. You changed the array?
So S4 is a subset of S2.
Oh, yeah. Yeah, let's just change this. Yeah, you're exactly right. I just want to do the example, not like introduce that it's not a Sperner family. So look at S1 and S4. Is there anything in common? No, they're completely disjoint. So what does that tell us if we fix this? So let's actually fix S2. And let's add S4 into our array. What is the S4 array going to be? Well, it's going to be 0, 0, 0, 1, 1. Well, now look at the S1 and the S4 column. What do you see? The first and the last one. You see 1 zeros everywhere and then 0 1s. And then the last row has zeros. Where's the 1, 1? It's gone. So what could we do? What we can do is this condition right here. It looks complicated, but here's the basic idea. The number of ones in each column is strictly more than half the number of rows. That's all it is. Or although it's not exactly that, but that's what it will be when we start making these. If I have every set in our collection have 3 values in it, which means that the vector has 3 ones, and I have 5 rows, could it be possible that 2 sets have nothing in common? The vectors don't have 1, 1 in those positions. If there are 3 values in every column, 3 ones in every column. We gotta fit pigeons into a bunch of holes. The pigeonhole principle. If there are 5 rows and each pair of columns has 3 ones in it, there must be some row where they overlap by the pigeonhole principle. So that if we ensure that that is true, we must have a covering array on x plus 1 rows where x is the ground set that we have, and then we added the row of all zeros at the very end. So I'm going to make a new page to tell you how to actually make these things. So instead of, yeah, go ahead.
Sorry, so you said that we don't need to have like all the ones and like when you're selecting the S's, like you don't need to have all ones because divisional?
I mean, you could. So if we're talking about the general case where you just have an arbitrary Sperner family, you could have a set with just all ones. But the thing is, that must be the only set. Because if you had another set, it's a subset of it. So yeah. I mean, you could, but it's just not going to be very helpful. Okay, so let's just look at 5 rows here. So the way that the 2K2 construction works is that you pick a number of rows in advance, and then you determine the number of columns after that. And what is the minimum number of ones that I can have so that it's at least half of 5? What is the minimum number? Well, what is half of 5? 2.5? What is the smallest integer above that? 3. So we're going to pick a bunch of columns that have exactly 3 ones in them. So let's see. Well, what could we do? Well, we can have a column of 0, 0, 1, 1, 1. What else could we have? Yeah. So we could have a 1, 0, 1, 0, 1. We could have 0, 1, 0, 1, 1, etc. And then let's just do one last one. So maybe 1, 1, 1, 0, 0. And what we're having here is every possible column with exactly 3 zeros. Every possible column with 3 zeros. Oh, yep. Thank you. Sometimes I go on autopilot. Thank you. Should be 3 ones. Well, another way I can phrase that is every possible column with exactly 2 zeros, but it's the same thing. Well, let's see. Well, is this a covering array? Or did we need to do something else in addition to this? What else did we need to do? Add the 0 row, exactly. So I'm just going to put it at top. It doesn't matter where I put it because as long as the interaction appears in some row, it doesn't matter. So I'm just going to put it at the top. Well, is this a covering array? And we can verify it is. Why? If you have the interaction involving 2 zeros, it's in the first row. Otherwise, it's either 0, 1, 1, 0, or 1, 1. 1, 1 must appear in every pair because every set of 3 ones here, every set must intersect in at least one position. But for the 0, 1, and 1, 0, it's a Sperner family because none of the columns is a duplicate, and no set of 3 is contained within another set of 3. Okay? So then that means that each set must have something that the other one doesn't, which means that we must see a 0, 1 and a 1, 0 in every pair of columns. Okay? So that's actually the whole construction. So you pick the number of rows, and you pick the smallest integer that's strictly more than half that number. What if we had 6 rows? How many ones in each column are we going to have this time? The number that's strictly more than half, which is what? 4. Because if I have 3, well, I might have a column with 3 ones up here and 3 ones down here, and they don't overlap. So, but if I pick 4, they must overlap. So then you add the row of all zeros once you make every possible column with exactly 3 or 4 ones, and then you add the zeros, and that's the whole construction. And so could it be feasible that we can do better than this? That we can have fewer rows? And it turns out it is feasible that it could be. But there's a result from a long time ago by Spencer and Cantona who independently proved that this is actually the best you can possibly do. You cannot do better than this. So, and can we do better on the number of columns? No, because we listed every column. So we cannot possibly do better. So this is an optimal construction. And it's super easy. You just list every possible column, add a row of zeros, and you're completely done. You don't have to verify anything. It's just a simple recipe.
So there's this like the Sperner family matrix thing.
Mm-hmm.
So the elements are in a subset, just a kind of like a ground example for constructing a covering array like this.
Exactly. So you can actually convert this back into a Sperner family if we label the other 5 rows, not the top one, but the other 5, the original 5, and then we can convert the characteristic vector back into a set. So for the first column, it would be 3, 4, 5, And then the second set would be, let's see, 1, 3, 5. Then the third one would be, let's see, 2, 3, 5, etc. And then the last one would be 1, 2, 3.
So you're just reducing this instruction to be Ashburner Family, basically?
It's not really a reduction in that sense of the word. It's just an equivalent formulation. Because if I have the array, you can make the Sperner family. If you have the Sperner family, you can make the array. And because you have to add the row of all zeros, and that's not part of the Sperner family definition.
Is it an optimal cover of strength too?
Yes.
Okay.
And 2 symbols, yes.
Okay.
So I'll see you all on Friday. Unless you're going to the problems session, in which point I'll see you in like 20 minutes.